Yeah, I want to do a quick gauge of the room, just out of interest of how much my topic will align to the audience. Who of you are Python developers here? That's a lot. Some Julia, I think, as well. That's very, oh, not too much. R? Right. Who are DataFrame users, Pandas users? Yeah, everybody uses Python, uses Pandas as well, I think. They go hand in hand. Anybody here are Polars users already? Yeah, the hands get it more and more. Anybody heard of Polars? Right. And are there some people who have dabbled in Rust already? Right. Okay, cool. That's sort of the topics of today. Not R, though, but also not Julia. Sorry about that. So my name is Ritchie Vink. I am the author of Polars, and I have a background in machine learning and software development, and since a couple of months, I'm also the founder of a company with the very original name Polars, and we are going to try to make something out of it. So today I want to give a short intro to Polars, a bit about what Polars is and what makes it different to what we already have in the landscape. I want to talk about Polars expressions, which are sort of the bread and butter of Polars. I'm going to talk a bit about optimizations, about parallelism, and we're going to finish with plugins. There's also a lot I'm not going to talk about. I'm not going to talk about how the engine works and all the cool stuff we do in there, but that could also be a good topic of a talk, but not for today. So what Polars is sort of a, I draw it, but I'm not really good at making these diagrams. It's sort of a Venn diagram. You have databases on one side, and you have data frames, typically known in Python. In R, you have data frames on one side, and Polars is sort of the synergy between both, because in my opinion, the most data frames out there were mostly seen as a data structure where you have a sort of a rectangular data structure and you apply some methods on it, right? So that's typically how data frames are being used. For data frames which are focusing on a single machine were typically used like this. So you have a materialization, a table with data and a schema, and you apply some operation, and this operation immediately materializes. And in Pandas, this also often is single-threaded. So that's why you see this single CPU core being used. And in my opinion, this is the wrong way we should look at data frames. I think data frames should be a way of thinking of data, a way of using them in our code, but the operation you do is super important as well. That should be part of the way of working. That should be stored as well. We shouldn't apply the operation immediately. No, we should store this operation as a data structure. And this operation, actually, this DAG of operations, this is at least as important as the data we get out of it, as the materialization. So in Polars, if you do an operation, this is also single-threaded. We take a schema and you get sort of a DAG with two schemas, right? And if you do another operation, we will extend this DAG. And the schemas can change in between, right? You can get different outputs of columns, different. If you do if you parse a string column into an integer, you will go from string to integer, so that will change. But then at the point you ask this operation to materialize, we take in two steps. We take the DAG of computation, and we first apply an optimization. Because now we have a holistic view of what you want to do. You want to read some data, but you only need two out of 10 columns. So let's only read the 2 columns that are needed. You only need to get the first 100,000 rows. Well, let's not read all of them. We can make these decisions now. Now we understand what you want to do. But if we would do things eagerly, we just had to do it because we first need to read, and then you apply the limit. And yeah, we already loaded the data. So by just being lazy, waiting a bit, we can optimize this query plan. And then afterwards, we go into materialization, and here Polars is designed from scratch. The second view is that this materialization is super important to do performantly, and to do stuff performantly, you have to be close to the metal, you have to be close to memory, and to be close to how you do parallelism. So Polars will do this often completely in parallel, and will go through great efforts to do this materialization also very fast. And what I mean by materialization is just a step going from query to output result. In a nutshell, we're sort of a database library that respects 50 years of database design. We looked at the database field, and they do a lot of, they've been thinking about this for a long time. And it seems that this, not by everyone, but the most dominant DataFrame libraries did ignore this research and just started from scratch and built methods on top of this materialization. And yeah, so what we did is we took the database research and applied it on DataFrames, and we see the DataFrames as a extension of that. And one thing we have is lazy evaluation, which gives us query optimization, and this gives you in the order of range 1 to 20 times speedups. It can actually be much more. It depends a bit on how much we can optimize. We minimize materializations. As I said, if you, for instance, if we see you do a sort followed by a limit, we can change the algorithm by a top K, for instance, and this saves a lot of materialization because you don't have to do the whole sort output and then take the first 100 rows. Yeah, the data types are constructed to amortize access and allocation costs. So we adhere to the arrow memory spec, but we are very careful in how often we construct those memory buffers. We try to reuse memory buffers. As a counterpoint, for instance, the current default string type in pandas are objects, just Python objects. If you have a Python object, it's a heap allocated thing somewhere else. If you want to read the thing, you need to go to memory, read it, and you have a cache miss. You go to the next string, you go somewhere else, you have a cache miss. This is 200 times slower just to traverse the memory. You also have a lot of memory fragmentation, a lot of wasted space between memory allocations, which you cannot use. So yeah, it's slow and it's expensive. It's written in Rust, so we have full control over memory, we have full control over threading, over the stuff that's important to control performance, over when we free memory, when we allocate memory. It's designed for effective parallelism. There are a lot of tools that do parallelism in Python, but I would argue that not everything is effective. If you first need to serialize a task and you need to send it to another Python process, and that Python process needs to serialize it, there is a big latency here. There's a big startup cost. Starting threads is also pretty costly. So if this latency is big, you can only parallelize large chunks of work, which works if you have easy parallelizable stuff. But for instance, if we do a group by needs to do some synchronization. It's not embarrassingly parallel. And when stuff is not embarrassingly parallel, you need to think more about what data structures you can use, how you can do the parallelism in a way that's yeah, you need to do stuff smarter, and you need to, or try to reduce synchronization, or try to make stuff weight free, or try to reduce latencies before you can do useful work. And it's designed for out-of-core processing. We're not at the stage we want to be yet, but we already have quite some support on it. Out-of-core means you can process data sets that are larger than your RAM size, and we do this by batching in loads. And for instance, in a group by, the cardinality of a data set is, if you do a group by, you go from n rows to the amount of groups. That's called the cardinality. So your cardinality can be way lower. A group by you can do a group by perfectly in batches, right? If the output size fits into memory, you can process this bigger data set because we don't have to load everything at once. But we also are able to spill to disk. So if we see that the output of a group by still doesn't fit into memory, we spill cold groups that are not used as much. We first spill to disk and keep hot groups in memory. And then when we materialize, we read them from disk and finish the aggregation. And we have very tight integration with I/O. That means that when we read something, we try to immediately read into our buffer so we don't have double copies, etc. So that's sort of in a nutshell, and it's a lot of information. I think one of the most important things we want to give is the Polars API, actually. Not the performance, not the Polars API is just as important. We try to make stuff predictable, composable, and our goal is that you learn a new expression language, and with this expression language, that it's somewhat akin to learning a programming language. If you learn a programming language, you learn the syntax, you learn the vocabulary. Those are often not so rich, but with, let's say, the Python vocabulary, it fits on two sheets of paper probably, but you can combine all those keywords and do anything you want, right? And with for loops, with indexing, you can do anything you want. And the idea in Polars is if we give you these expressions and you can apply these expressions everywhere, you can combine them and do a lot more than what's, for instance, possible with pandas. With pandas, it's super common that you need to go to a lambda, to a custom, to an apply function, because the pandas API doesn't give you the functionality to do it without going into Python. But once you go into Python, you are GIL bound, because we have the GIL, the global interpreter lock. You cannot do any multi-threading. You need to materialize into NumPy or you need to materialize something to give the user something it can use. So you lose parallelism, you do a lot of expensive materializations. So the goal in Polars is giving you an API so you don't need to go back to custom lambdas as much as you needed to. And the most common the important thing here are expressions. Expressions are composable functions which take in a state of a data frame, a state of another series, so another argument, and it can take in the state of a group. So if you're in a group by, you have a group state, but if you're not in a group by, you don't have it, so it's optional. And from this state, it produces an output, and they are composable. And the inputs can mean things. Okay, for instance, I take column foo and I take the sum, then in a select, we just sum the column, but in a group by, we sum the group, right? So the input can mean something different. But if we do this over list elements, we sum the list elements instead of the column. Or if you apply this over, you can also apply it over literal. So what the input means differs depending on the context. So this is, what do you want to see here? Yeah, they are first-class citizens. That means you can use expressions in all the important operations. So if you select columns, you can use expressions. Or if you want to add columns, you can use expressions. But you can also do it in a group by. So you want to group by this expression. So I want to group by column food times 10 modulo 20. You can use it in aggregations. This is a cool one. You can also use it in a pivot. So here you see we do an aggregation function, and we say we take the cumulative sum, and then we take only the head. If you want to do something like this in pandas, you need to apply a lambda. You need to use a custom function. So these first-class citizens, you can pass them in many operations, and we will execute them in parallel and fast. So that's sort of the promise. And we are very serious about using expressions. Actually, we're so serious that if we see that you are, so map elements is, when you map elements, you apply a custom function, a Python function to to every element. This will be slow because you will running a Python function. And if we see that you're running a Python function for something you could have done in polars with an expression, we actually give you a user warning and say, hey, we've seen you use this function, this Python lambda. You can replace it with this expression, and then it will run vectorized and fast. And so, yeah, and afterwards we replace it, and we get the same output, but now fast. So it's pretty cool what we do here. So your Python converts into bytecode, and we deconstruct that bytecode and say, hey, we can do quite some. We can recognize some NumPy stuff. We can recognize arithmetic, etc. So. Thank you. Yeah. So with the API of Polars, we want to make a promise that if you use our API idiomatically, you will get one thing, that's C speed, and we're all accustomed to this, right? If we use NumPy, we get C speed. We call this vectorization in NumPy. You will get another thing, you will get optimizations, and you will get parallelism, and you might get out-of-core processing. Eventually, you will get that. We're building that. And I want to argue that this is slightly less than what we're used to with NumPy. With NumPy, we already got the C performance. But with NumPy, we didn't get any optimizations. NumPy is eager. So if you do any operation multiple times, NumPy will just execute it. And there is no query optimizer. There's no... But if you would write a query, you would write a program in C, the C program would get optimized, right? And the optimizer will recognize if you multiply a column times 1, it will elide this times 1 because it doesn't do anything. But if you do it in NumPy, it will happily just multiply times 1 because... So we, of course, are not the JIT compiler, but you do get optimizations from our expression engine. So it gets you more than what you get with normal vectorization. You get query optimization. And this query optimization can be worth it because we're working on columns of typically millions of rows. If we can elide some operations that were not useful or not change the result, it can save a lot of compute. Here's an example query. We scan a Parquet file. Scan means, okay, read the Parquet file, but when I ask you to execute this, you need to read this Parquet file, but currently you need to just return me a DAG. And from this DAG, we call this a lazy frame. From this lazy frame, you can continue with writing your query. And afterwards, you apply a filter, then you apply a group by, and then you do an aggregation where we compute the mean and the sum. And just to give you an example of what optimization can do for you. First, we run this query without optimization and it takes 1.7 seconds. You can see it runs in parallel because the CPU time is 5.5 seconds. So the CPU time is sort of the time the CPUs have taken if they would run after each other, but they are actually running in the same time. So the wall time, that's the one below. That's the time we observed. The time we observed was only 1.7 seconds, 0.07. But if you run this query with optimization, it only takes 230 milliseconds. So you get this for free. You don't have to do anything. So what has happened here, Polars has recognized that we can apply the filter actually at the Parquet file. And at the Parquet file, there can be statistics. And sometimes we can prove, hey, if we apply this filter, these statistics show that this data is not in this row group. We can skip this. Or we can apply this filter very soon and don't have to do the materialization of all the columns. The same counts for just selecting the columns we need. A Parquet is columnar, so we can just select the columns we need. And that saves a lot of deserialization, a lot of I/O reading. There's also another optimization here, common sub-expression elimination, which I will explain a bit later. Here it is. As we see here, there is we apply the mean and the sum, of L quantity times extended price. And we see that we do this multiplication twice, right? So if you would be worried about performance, you might have put that computation first and then did another with columns. And here it's trivial to see, but once you get into more and more complicated expressions, and those things can be recursive, it gets more complicated to see where I did double stuff. Actually, you don't have to worry about this because polars will recognize it. And polars will recognize common sub-expressions, we call them. And we will pre-compute them, cache them, and then cache them for as long as the context from the with columns exists. So the multiplication, there will not be a redundant computation here. We do the same with query plans. So in a query plan, if you, for instance, read a part of a file, you do some computation, and then you have a subtree of your DAG, and then you self-join that, then actually you would do twice the same, right? You would, both branches of the join would do the same operation. So we recognize this, and we cache the first join, or the first part, and continue from there. You could do this manually, but you don't have to. So the idea is with optimizations, we take this responsibility from the programmer. There are also optimizations we can do internally you cannot do as a user because you don't have full control over memory or over swapping out stuff. Here are some of the optimizations we do. These are single pass optimization. The first one is schema checks. I love this one because I really hate it when my when my pipeline fails 20 minutes in. When I'm 20 minutes in and I'm indexing something with a floating point where it should have been an integer, we could have checked that up front. So we try to fail early in polars. We try to be strict. So you will get the hangover up front instead of the day after. So another one's projection pushdown. This means we only read the columns we need. Predicate pushdown means we apply the filter as soon as possible. If you filter rows before you do a join, the join will be cheaper because you put less rows in a hash table, for instance. We do some join branch reordering because it's cheaper to only build the smaller table. We do scan sharing, as I explained, if it's the common subplan elimination. And type coercion. Yeah, we try to make sure that the types match, and otherwise it's sort of similar to the schema checks. And I want to talk a bit today about not how our engine works, but more how our parallelism works. And our parallelism is used we have two engines, and they actually use the same parallelism scheme. And we use a single thread pool. So in polars, we keep a thread pool alive. And let's say you have the default size of your thread pool is the amount of cores on your CPU. So my machine has got 16 cores, so it starts with 16 threads. And every core will get a dedicated queue, a queue of tasks. And on this queue, we can publish tasks. And this publishing tasks on the queue is very cheap. We just publish a function pointer on the queue. There's no serialization here. There's no spinning up a thread, and the queue will just keep doing work, right? If there is available work, it will process it and return the result. There's no, as I said, no thread startup cost. Stealing work does require some temporary locking, so there are some mutexes involved. There is a slide overhead, so if you're talking about data frames where you have 100 rows, then the serialization, the parallelism might have a little bit overhead, but then we're talking about counting microseconds anyway. There it doesn't matter that much. And we try to minimize this, but there's no contention between threads. And this is important because if you have more, let's say you start a thread for every parallel task you have, and you have 1,000 threads running, then the OS will swap between the threads and will try to give every thread some work to do. But this swapping is super expensive. It needs to clear context, clear memory. So you don't want the OS swapping out threads. There's no contention. And we have a protocol called work stealing. That means that if a thread is finished or a core is finished with its queue, it finished all its tasks. It doesn't have any tasks anymore. That's in the second image. It will steal some work from another queue. It will split the work from another queue, take that work, and keep continuing their work. And with this, Polars is very good at keeping all your cores saturated with useful work. The only important part is that we publish tasks that are some sort of similar sized, right? You can imagine if you have one task that takes 100x the time of the other task, then you would be single-threaded. So what we try to do is devise the work, make the work divisible in smaller tasks. Here's an example of how Polars does this splitting of work. If we create a data frame with some integers and then we take the modulo of 1 million, so we get 1 million groups, and then we create some random integers. If we want to compute the unique integers in a select context, so we just take one column and we want to compute the number of unique elements. This number of unique elements, this is an expensive operation. We know we can parallelize this. So we parallelize this over the 3 cores we have, but the multiply times 2 is actually super cheap. So we know that this multiplication is not so expensive, so we will actually not parallelize this multiplication and just do it on a single column. It's not worth it doing the multiplication. The same in a group by. In a group by, it depends on the group. We have different group by strategies, but let's say you have 1 million groups, then you have a lot of groups, way more groups than you have threads. We actually finish the aggregation of every group in parallel, but then it wouldn't make sense to also parallelize this n unique within the group, right? Otherwise you have parallelism on parallelism and you would explode the number of tasks. So at this point, the n unique wouldn't split into extra parallelism because that would create extra overhead. So, and again, the multiplication on the result is super cheap. So even though we do a group by, we can actually ignore the groups and just multiply the output of every group immediately without doing any parallelism. So it's totally not important for a user, but it's more Polars tries to split the parallelism for you. You don't have to think about it. You just write your query. Yeah, the parallelism, the thread pool is not bound to one query. So there's a work scheduler. That means you can use Polars behind a work scheduler like Airflow or web server because the tasks just get published on a queue, and then there will no be contention. There will be no contention. So that makes it useful for that. And third, the promise you will get performance. So yeah, Polars is a vectorized query engine. It's written from scratch in Rust. We go through a lot of effort to have good algorithms, but also to just implement things. We want to be as fast as the OLAP database engines, and that's how serious we are about performance. Yeah, I'm going to go a little bit faster because I want to get to the plugins. But Polars is super fast. Here are some results from the TPCH benchmark. The TPCH benchmark is a benchmark made for databases. It actually fits databases more than DataFrames, I would say. But Polars performs really good here. You can see more on a benchmark. There's also a benchmark made by DuckDB, also a super fast engine, where you can see it on their website. Polars is also one of the most performing engines there. Yeah, plugins. So I talked a bit about this parallelism and how you get this with using expressions, but we try to be really good in being composable and and not needing custom Python functions. But I know the real world there's always something you need that you cannot do in our API. You have some business logic, you do some strange machine learning, which we cannot support. We cannot do any, I don't know, neural net fitting or something exotic. I cannot even imagine what kind of scientific formulas there are. Well, formulas you can actually do pretty good in expressions, but there's always some business logic you cannot do, and you need to refrain to UDFs, right? To user-defined functions. And the plugins is a way to do this as if it was a native expression. So with a plugin, you get native performance, you get Rust performance, you get native integration because the plugin will run. You can compile the plugin and you can then register the plugin to the Polars engine. And the Polars engine will run the expression as if it was its own. And it will enable from optimizations, it will benefit from parallelism, and it will be fast. And so you have no GIL, for instance. And as an example, I want to build a pig-let-in converter. So pig-let-in is a silly language where you take the first letter of a word, you swap it, you put it at the end, so pig. If you take the first letter P, it's going to be ik P, and then you always end with I to make it sort of what pirates do. So pig-let-in would become ik pi add-in lay. Easy, right? Okay, now let me find my mouse. So, and let me find, oh, this is hard. Yeah. So 5 minutes, we can do this. So I'm going to go a little bit. So this is some Rust code that takes a string and converts it to pig-let-in. You just have to believe me, this is how you can write that function. You can write this function in Rust. And then you can expose this function in an expression. You create your pig-let-inify expression. It takes as input a series, and it takes as input some quarks, keyword arguments from Python, which you get automatically deserialized. So you can create a struct and put anything in there, and we will deserialize this keyword arguments from Python into that struct in Rust, and then you can use it. And here we apply this function. And then the only magic here is we say, okay, this is going to be a Polars expression, and the output type will be UTF-8. You can also provide a function here which will say what the output type will be. For Polars, it's important that we know the output type because we need to do optimizations. To be able to do that, we need to know what we have, right? Can I zoom in? Man, you ask a lot. Sorry, can I zoom in? I don't know. I don't know. Not within the time I have. I'm going to explain it a little bit. I'm going to walk you through it. So you can compile this expression. I pre-compiled it, but at that point you can just create a class language where you say, okay, this language has got a pig-let-inify expression, you wrap it, and then this is the only boilerplate you need. I'm going to share my slides afterwards, sorry for the, and this is the only thing you need, and then you can compile it, and then we go into the, Python world, back to the Python world. So let me get my mouse. So here we have we're back in Python world. We have a Jupyter notebook. Is this readable? Ish. I can zoom in here better, I think. Here's Control Plus, right? No. Help me. Ah. View.
Presentation mode up top. Third one.
Yeah? Okay. Did it make a difference? Yeah, did it? Oh, okay. I'm going to read some Poké file, and I'm going to read the comments, and I'm going to create many columns with some text, just to get a lot of data points. So here it is. Now we have 16 columns with 5 million strings, and strings are very expensive data types. And it means we have 80 million data points, and we want to make this pig-Latin converter, and the naive way to do this would be doing this in Python, right? You would write a Python function, and then you use, so in Polars you can select columns with an expression, so we select all columns that start with the comments name, and then we apply this function, and then we output it. So let me make it a bit more interesting by, this is challenging. Here we can see, on the top you see my CPU, you see my memory usage, and let's run this thing. And I don't know why, this thing will be slow, I know why that is, but there is also some stack behavior in memory. It seems that because of the Python GIL and the Parallelism, every column gets a bit of work and builds its thing, but just when the last column finishes, it can release the memory again of the temporary state. So actually, because of the Python GIL locking, it seems that every time another column gets work to do. But yeah, it was slow, it took a lot of memory. It took 22 seconds, right? A better way would be writing a Polars expression. We can just write a Polars expression. So we slice, and then, so we first take the first, if we have pig, we slice, so we get ik, and then we put the first letter on at the end, and then we end with I, right? Is this readable? So this is a Polars expression. This would be a better way. So this should be bigger. I cannot. So this would be faster. Well, it's finished. It's a lot faster. We saw there was a lot of parallelization. We didn't saw any memory bump. And the wall time was 800 milliseconds. But we want to build the fastest pig-Latin converter we have, so we use the Polars plugins. And to use the Polars plugin, we can just import our library, pig-Latin. That's it. And now it's available as a pig namespace on an expression, and we can run this thing. And this took 330 milliseconds. So we had to get a speed up of 2.5 by, so we go from 22 to 800 milliseconds to 350 milliseconds. So the speed ups are very clear. The memory consumption is a lot better, and parallelism is very good. So in this case, you could have done it with an expression, but there's also a lot of, once you do more exotic stuff or your own business logic, you're going to build hash maps. I don't know, then it's going to be, for instance, if you do anything cumulative, then it's going to be hard with the DataFrame, right? To express cumulative, if we don't support it, so we do support a cumulative sum, but if you have a cumulative, I don't know what kind of statistic, cumulative median, or then it's going to be, I don't know, I'm making something up. Then it's going to be harder. So this is what I wanted to show about expressions. I'm going to go slightly back to the presentation to have my last words. It's not that. It's not that much. Oh man, it's also going in the wrong direction. Well, thank you. There's one thing I want to ask. If you want to try out Polars and you're learning, we have a very active Discord with people, people helping each other out a lot. So if you want to say hi in Discord and learn more, be welcome.
So thank you, Ritchie, for your talk. Right now we're going to take some questions. Well, as I am the moderator today, I get the chance to have the first question.
Yeah.
So I was actually wondering how you got started on polars, right? So you've told us a lot about how polars works, but how did you actually end up there?
Yeah, well, it's a story of changing goals, I would say. I was dabbing in Rust, and I needed to join I built something in a web server, and I needed to join 2 files, which normally I would do with pandas. But there wasn't a DataFrame library in Rust. I thought, oh, let's import the DataFrame library, being accustomed to the Python landscape. And then there wasn't anything, so I thought, oh, how hard can it be to write a join? So did some research. It was super slow. Did some benchmarking with pandas. I thought, okay, this is really slow. Okay, how can I make it a bit faster? And as I went, you start learning about joins, about relational stuff. You learn about databases, and I thought at a point I wanted to make it lazy, and at that point I really started coming up with the query engine stuff, and that's sort of akin to what an interpreter is. And when that started rolling, yeah, the more I learned about what kind of cool stuff databases did, and I thought, oh, okay, we need to do this differently. Yeah. But it started as a hobby project, and it was a hobby project certainly for a year. It wasn't. I didn't think anything serious of it back in the day.
Completely escalated.
Yeah. Yeah. Oh, but awesome. The last 2 years, at a point, we're like, okay. I think we can. You learn more. You think, hey, okay, I think we can make stuff better, because it doesn't make much sense how we first tried to do the Pandas API, for instance, and that became super hard because it's super inconsistent to predict what it will output. And then once you want to do anything in parallel, the Pandas API didn't make that easy. If you want to do stuff lazy, it just made stuff hard. And the further we got, we thought, okay, why not start from scratch and build something that we think is the best way to do it? And it became more opinionated, and I thought, okay, this is how I think you should work with data. Not that we're there yet, but we wanted to start from scratch and just have a clean slate and think logically, how would you use, what would data frames look like if we want to use all the threads on your machine and you want to utilize your hardware from scratch, while learning from what the database engines did. Yeah.
Awesome, thanks. So are there any questions in the room? Over here. So we've got a microphone.
It's going to be thrown at you. It's going to be thrown at you.
Over here.
Throw it at the guy. Throw.
Thanks.
We got it. Okay.
Awesome.
Thank you for the talk, Ritchie. I had a question about the choice of Rust. Sorry. Looking back, do you think the choice you made was a deliberate choice, say compared to C++, or do you think if you didn't have Rust and you would have to do it in C++ or a different language, how would you benefit, or how much did you benefit from Rust? Sorry.
Rust. So the choice wasn't deliberate because I just was dabbling in Rust at the time. If Rust wasn't there and I deliberately built a DataFrame library, I don't think I would have built one, but let's say I wanted to build one, I think C++ would be a good choice. Though, I think Rust is a better choice currently with what we have, because Rust has got a concept called borrow checking, and borrow checking has got some guarantees that you cannot, get seg faults, get undefined behavior, bad behavior, if you use the safe language, which we don't always use because we care about performance, but the amount of unsafe is way less than the amount of safe code. And so That makes it a lot easier, but another thing that makes it super, I think the borrow checker guarantees that the same guarantees about memory also give you guarantees about deadlocks, about multi-threading. And multi-threading is insanely hard, debugging multi-threaded code and just having race conditions. And once you start building a complicated engine and you have all kinds of stuff happening, stuff gets really hard. And I know from a story that Firefox tried this in C++ with the Silver engine, and they failed, I believe, 3 times, and they were able to complete the refactor with Rust, because in Rust it doesn't compile if you send something mutable to another thread and both threads can mutate it, for instance. It just doesn't compile, and it explodes in your face up front, and then you have to rethink your design. But it will prevent you from building something unmaintainable in the end. So I think if you go multi-threaded, I think Rust is a very good choice. Yeah.
Thank you.
But it was not deliberate.
Okay.
Right, yeah. You can throw it to me. Are there any more questions? All right, so I'm going to take 2 more, and then we're going to have to wrap up, because there are other sessions waiting as well. Yeah, there it goes. Ooh. First throw of the day. Sorry, guys.
Is this working? Yeah. Are there any like existing or planned features that support like distributed, like multi-worker processing? Is there any desire to like compete with like Spark on that front, or no?
Yes, and so we started a company. So our goal for Polars is empower your laptop, empower your single machine, and we think vertical scaling is going to be way more important. I think up to 1 terabyte, I think in the future, you distribute it, it will be hard to beat vertical scaling, I think. But we are also going to make a Polars Cloud solution, and with this, we want to make some sort of a hybrid where I don't think the Spark solution with always going horizontal is the optimal. I think there should be some hybrid where we can say, okay, we want to vertically scale, but in this query, it's probably useful to do some batch work. But that's something we didn't start yet. We still have to figure out. And so I cannot comment too much on it. But yeah, there are some goals.
Thank you. So there's a question in the back. Not sure if your aim is any good.
Last question. All right. Then we'll give time for everyone to find their next group. Okay.
Still works? Yes, there we go. Thank you, Ritchie, for the talk. I was wondering, there are all kind of new features coming up or already existing in later versions of Python, like creating new interpreters with their own GIL.
Yeah.
And would that affect, and have you thought about that in Polars? And are you also involved in, let's say, steering new developments in Python?
No, it shouldn't matter much for Polars because we don't want you to use Python. We want you to use Python. We want you to use Python, but we don't want you to use Python functions to use Polars. Because even when there is a GIL per thread, you're still running Python code. So use expressions or use plugins. So use Python I think Python is a great duct tape language. Use Python to get into C, or to get into Rust, or to get into C++. If you do anything performance critical, I think you should use Python as a duct tape language. Yeah.
Awesome. Thank you.
Thank you.
Last round of applause for Ritchie.